So we'll talk about the final at the end of class today, and in theory, we will finish these slides. We should be able to. Okay, so recap. Chapter 17, probably the most difficult chapter. There's so much going on, so many things combined together. It's a good example of how to use the data science library, right? So, okay, classification is the idea of predicting a categorical variable. Spam or not spam? Is this pixel a stop sign? Is it part of the road? Is it part of the double yellow line that I should not be crossing? Etc., etc. One way of making a classifier, which is something that does classification, is to use the nearest neighbor classifier. And so we imagine that all of our data in our data set is just a point. Each piece of data is another point in a very high dimensional space. Doesn't have to just be 2D. And the goal of the nearest neighbor classifier is to go and find, like, you give me some new point in the space, some new data value that you don't know the class of, because maybe it's like a patient that you haven't seen before, but you've taken some data from other patients, something like that. And you go off and you're like, all right, this new point, the rainbow point, right? Go put it in the space and go find like the k nearest things to it using a distance formula. So we have our nice distance formula, and that generalizes to multi-dimensional distance. We know that and love it now. And so you pick a k value, it should be odd. Pick that many nearest neighbors to go and find, maybe 3, and go look at the classes of those next to the new point, and use the majority class to predict the class of the point that you're not sure about yet, because you don't have any concrete data on that. You want to use this as prediction. So that's what the k nearest neighbors classifier is all about. You find the k nearest neighbors where you pick k. It's up to you, some odd number, and you take the majority of the k nearest neighbors, see what their classes were, and if it's just 2, you just pick the one that has more. If there's more than 2 classes, you can pick like the one that's most popular still, but maybe there's not a majority. There's other things that you could be doing. Yeah, assign the point to the class that wins that majority vote, and don't use like k equals 2, because then if it's green versus blue, you can't like make it whatever that those 2 colors together create. Greenish blue. Not possible. Okay, so that's k nearest neighbors. We know it, we love it, and the whole the job of like figuring out if our k nearest neighbors classifier did well is we took care to take our entire data set and split it, right? We did that. We did that splitting process. We made a training set. That's what we created the not neural network, sorry. NN can mean neural network, and so I have that in my mind as well. The nearest neighbors classifier based on the training sets, like going and finding things based the closest things in the training set. And then we saved away stuff in the test set to test whether our classifier using the training set did things correctly. We just like forget about the label for every test thing. You go use it for prediction, use the training set to predict with your k nearest neighbors, and then you look at the actual label for the test set. Did we get it right or not? And that's how you can evaluate your classifier. So that's what we did for the very last example of the day, which was about breast cancer. And we found that our k nearest neighbors classifier, where we split the training set and the test set in half, pretty much perfectly, was almost 100% accurate in determining class 1 or class 0, whatever that meant. If it was like malignant versus benign cancer, or one type of cancer versus another type of cancer, something like that. So that's the story so far. Are we ready to continue the story? All right. So yeah, that's most of it. Honestly, the last piece of the puzzle that's where we stopped. You can do a little bit more, and it's kind of cool. All right, so let's go there. So you can do regression, actually. You can use nearest neighbors to predict values. And honestly, we've kind of done that already. But you can think about it in this large space now instead of just like, we technically did nearest neighbors for predicting the height of a sun. Remember that? We did that. So you can generalize that idea. So that's called, and when you're using like more than just 2 variables or more than one variable to predict another, it's called multiple regression. So we know about linear regression. So regression just in general, right? It's a word that means we're predicting a numerical value. Okay, we're trying to predict a number rather than a categorical thing. So this is switching gears now. All right. So we know about linear regression, where we have an x value predicting a y value. It's like you're drawing a line. You're trying the best fit line, right? Come on, PowerPoint. There we go. You're trying to draw the best fit line between things like that. whatever it is. So that is linear regression, but that looks exactly like the blue dots. Let's fix that. So linear regression is trying to find the best line between all your points. Something like that. Okay? And so you're using, you give me an x, you predict a y. That's what you do. That's how that works. That's linear regression. It's only two variables are involved, right? Multiple regression, on the other hand, is I've got some large multi-dimensional value, like we've been using for classification. I've got some maybe 3D point, 4D point, 5D point. Go and find the closest hyperplane that predicts all those points. That's what we're looking for, kind of. That's one thing you can do, but that's multiple regression. There's when you use multiple variables at once, like you use a point in a multi-dimensional space to predict the class or like a number, then that is called multiple regression. You use multiple attributes to predict numerical values. Linear regression is you use one attribute to predict numerical values. That's the only difference. And so multiple linear regression is a thing. Multiple regression using nearest neighbors is a thing. And those are actually the two that I want to show you. All right, does that make a little bit of sense? It's like, all right, instead of just one variable, instead of using one attribute to predict a numerical value, like this is an interesting, I don't know where I got this. I got this from Google. What are they trying to predict? TV expenses predicting sales? I have no idea what that means. Interesting. Sales of what? So yeah, that's the difference. So using multiple attributes to predict numerical values, and a good example is houses. So you go on Zillow, you can see a lot of numerical data on houses, right? Like, right, this house has this many square feet. It has a garage that's this size. It has this many cars. It can hold this many cars. It has an upstairs that's this many square feet, and downstairs that's this many square feet. So you got a lot of data that's numerical, and so we can do multiple regression on that to predict the price that a house might sell for. That's what we want. Okay, so that's the example for this time for data, for our data set. Okay, we've got multiple regression. Oh, what? No, what? I don't even know what I pressed. Weird. So multiple regression where, remember that the idea of regression is just it's a term, right? Regression is the generic term meaning to predict that means to predict a numerical variable. So that's what we're doing. We're just doing regression, but using multiple data points all at once to predict stuff. So let's see. I'm going to include a data set called house.csv in the data folder. I'm going to do some weird things with it though. So let me just copy and paste those weird things. So that's what I want. All this weird stuff. So I'm really just including this data set, house.csv, and it's got a bunch of things. We're going to do only one family houses. We're going to do only normal houses, not like foreclosures or things. And then we're going to take these features. All right. So here, if you want to play along, let me give you this code right now. Dun, dun, dun. I'll probably have to keep on giving you code, but something like that. If you refresh our chapter 17 page, you should have what I just gave us there. So that's our sales data for houses, apparently. So like here is the square foot of the first floor. Some of them don't have second floors, but if they do, like that's how many square feet it was. There's a basement, this is how many square feet. It's the area of the garage. If there's a wooden deck, I guess that increases the value of a house probably. There's a porch, that's at square feet. The area of the lot, and probably square feet as well. The year the house was built, and the year it was last sold. Something like that. And then here is the current sale price, something like that. So there, that is like it just got sold in some, like now let's pretend. So that is, I think, what we want. And so the thing that we want to predict is sale price. Does that kind of make sense? Given all these other things, given all this other information about the house, predict how much it's going to sell for now. Yeah. Honestly, years sold could mean like the price, like that was the price. This sale price was the price it was when it was sold. I can't remember. We can assume that actually. That would be fine too. That would make more sense for like that 2010 is a little bit bigger than the 2009. So it doesn't matter. We're using these other data points. We'd like to use them all to predict the sale price. So I want to kind of cover this up for a second and see how well we can get, how close we can get to those. Okay. So with that in mind, with these particular kinds of prices, we've selected some things out of this original data set. Like some of them were foreclosures, some of them were not single family housing, some of them were like office spaces or something. Like with those, we'll call them sales. Let's see what we're looking at. What's the sale price? How does it vary? Let's make a histogram. We'll do 32 bins, and the unit is dollars. Sold for that many dollars. So it looks like whenever they made this data set, probably around 2010 or something, the houses were, maybe the median value of the house was about $150,000 that it sold for. If only it was like that still. But that's what we're looking at there. And so the question is, can we predict the sale price, the price that the house sells for, using some of this data? Honestly, using all of this data. Some of these values you can imagine are very heavily correlated. So like you could imagine the square footage of the first floor, like if there's more, that's going to be a higher sale price, right? So you can start drawing scatter plots. You can be like, all right, sales dot scatter first floor FLR square feet to sales price, L price. There it is. You can see that's decently correlated, yeah? But it's still not perfect. If you try to draw a line here through it, like it wouldn't be great, right? It wouldn't be very accurate for a good chunk of the houses, right? Especially as you get larger and larger, it kind of probably depends on location at that point, and you get more a more varied spectrum there. So, okay, let's see what the correlation is for at least those. Dun, dun, dun. So I'm just gonna copy and paste. Boop, 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 we did that. I need this. We need our standard, convert to standard units, because that lets us do our correlation calculation, right? Because that's going to be the average of the product of the standard units, right? So that's what we're doing. And so let's do that. Let's do the correlation of sale price to first floor square footage. All right. It's 0.6. That's decently large. That's a very good correlation. But the whole point of this new topic is multiple regression. We could probably do better if we used more data, right? We could probably do better if we use more data. So let's see what that looks like. So here, idea, right? This is decent. It's not 1 though. It's just 0.6. So idea. We could use all the numerical attributes to predict the sale price. That's what we would like to do, all right? That would probably correlate even better. That is the goal, okay? And so enter different options. You can do multiple linear regression to use like something like a line, but in multidimensional space. You could also do k-nearest neighbors for multiple regression. I'll show you both, all right? So this will get a little ugly and weird, but it's an interesting idea. Multiple linear regression. So this has nothing to do with nearest neighbors, but it's still cool to think about. This is one option, all right? So one thing we can do is we can go through, because we always want to know like what correlates the best. That's our goal. What correlates the best with the sale price? We can go through every other label. We can be like, sales.labels, like sales is the table, .labels is the labels, and I can iterate through those with a for loop. I can be like, all right, for every label in sales.labels, here's what I want to do with it. I would like to go and give back the correlation between sale price and that label, right? That would be nice. And I can print it out in a pretty way. Like, let's go see who's correlated the best, okay? That is what I want. And sorry, it's correlation with the sales table on that label on the sales price. So let's print that out. Print. So the correlation of the label, you just like, if you put commas, it puts spaces between things when you give it to print. Correlation of label and sale price, colon space, something like that. Okay. And if I press enter, I get all these values. Nice. I guess I didn't need this colon right here because it just adds a space for me naturally. So obviously sale price and sale price is perfectly correlated. First floor square footage is, I guess, the highest. Garage area is also very good at predicting the sale price. Impressive. Oh wait, no, basement. If there's a basement, that predicts it very well. Apparently, that's very highly correlated. That's good to know. And then year built, like a later house is probably going to sell for more. That makes more sense. So yeah, that's a thing. But you can see like a lot of these are all correlated. These are all positively correlated. One goes up, like the square footage of the second floor goes up, you are going to increase in the sale price. It's just not perfectly correlated. Yeah. So wouldn't it be nice if we used just like more than the first floor? That's what I'm trying to argue in favor of right now. So like we can get the square footage of both floors by doing this, right? We can be like sales dot, well here, sales dot column 1, like 0, 1, and 2. So if I add column 1 to column 2, I get the total square footage, right? Sales dot column 1. If I take that and add it to sales dot column 2, that's the total square footage of both floors. Maybe there's 3 floors, who knows? But at least the first 2. There's both floors, they're total. We can get the correlation of that, right? Correlation of sales with a new column called both floors. That's that. Give me the correlation between sale price, and both floors. That's the new thing I just added to that table. That correlation is higher than the others at 0.78. So that just goes to show that it's good to combine more features. That gives you a better correlation, yeah? And it's linearly correlated too. That's quite nice. So it's better, moral of the story, it's better to combine multiple attributes. Don't just use one to predict the sale price, use a couple, use them all. So let's try to use them all. Let's try to combine them all. I hope that's good motivation. Okay? Are there any questions about what I've just shown you? It's like we should try to use every single feature we have to predict the sale price. Some combination of them. You can add them, that's probably fine. But let's do something akin to linear regression. Let's do multiple regression, okay? So here's our thoughts. We're going to need to do, again, we're going to make a training set and a test set. Here's how we can do it. So how many rows are in sales? 2002, that's an even number. So I guess we could split it in 2 very perfectly, just like get the first 1001. If you wanted to do this programmatically, like make a function that makes a test set and a training set for you, you could. It would be complicated if you were trying to split it up and it was an odd number though. Because like if it was 2003, you try to divide by 2, this is not an actual index, right? When you're trying to do indexing and like take pieces of sales, like go to do the dot take method. So that's hard. Here's the secret. Say you wanted to split up into thirds or something, like take 1/3 for the test set and the remaining 2/3 for the training set. So you divide it by like 3. That won't go in cleanly. So when you do the slash in Python, it gives you back a float. You can't use that as an index. There's no index 667.333, right? Can't use this as an index. Something you can do in Python, though, is you could say, instead of just a single slash, you can do a double slash. And what that does is it's a division that gives you back an int. It's going to chop off the decimal places. It's not going to round it. It's a little weird, but that's a way to do division and always get an int back. an int. You can always use that as an index. That is lovely. All right. So that's a way to programmatically, like, let's chop up whatever data set I have into some pieces, because you can always just do //2 and get a whole number. And that can be an index, like go up to that index. Okay. So, okay, I want to make a training set and a test set because I want to do prediction. I want to predict the sale price. So let's, the first step is to shuffle the sales. Shuffle all the rows of sales. Don't like keep the original order. So shuffled sales is sales.take a sample of all the things in it, just with replacement equals false. Don't duplicate anything. Give me as many as there were, just in a different order. All right. So I've shuffled it. Let's make a training set. I'll call it train. And that will be, let's do the first half. So that's shuffled sales.take and np.arange. If I want to go to the first half of it, I know it's just 1001, but if I didn't know that, arange, go up to index 1001, but not quite. You just go up to what you put in here is sales.numRows //2. That will always work. That will always give you an int back, even if it was an odd size thing. Does that make sense? That's nice. You can make a program that does that no matter what you had in your table. It's like make a function that took at the table and called it t or something. Like you could always get your training set that way and your test set pretty much in the same way. Because the test set is like take from this index onwards, right? Until the end. So take, starting from this index now, because this one goes up to but not including that index. That's perfect. 0 to that, -1. This one starts here, and we want to go to size -1, right? Because the last index of sale, the last row is index 0 all the way to 2001, right? So you can just say sales numRows here. That's perfect, because the last, when you do arange, it gives you up to but not including that thing. So that's beautiful. I've just got the right amount here, yeah? So like train.numRows and test.numRows. Like I've made two tables of shuffled things. They are both 1001. I've split it up. And so you can probably make a function that like takes a table that makes a training set and a test set for you that way, okay? Because you never need to know like, oh, was it a whole number? Do I need to round? Just do the //. It'll take care of that for you. So yeah, that is the goal. And now what we'd like to do is to do multiple linear regression. So remember that the idea of linear regression here, the idea of linear regression is, gosh, how do I want to do this? The idea of linear regression was we wanted to find a slope and an intercept, right? Like for every y, we wanted to predict, like we wanted to learn an m, like given any x, and we wanted to learn a b, right? That best predicts the data we have, right? That's what linear regression is all about. We want to learn this guy and this guy, yeah? So that for any x, I give you the best y. For any input x, I give you the best y. That's the output, yeah? That's what I'd like. For multiple regression, if you're going to try to use a bunch of data at once, you are mostly doing the same thing, but in a fancy way, all right? So what's going to happen is we have all this data, right? We've got how many things? 1, 2, 3, 4, 5, 6, 7, 8. I've got a 9-dimensional point now, right? So I'd like to somehow make slopes for all of those, more or less, to have them predict the sale price. I'd like to do something like this. Instead of all that, I want to turn this idea into predicting sale price by like doing the first like m1 times x1, like the first thing I want to discover a slope for the first variable, and like another slope for the second variable, m2 x2 plus m3 x3, all the way down to, I guess there were 9 of them, right? m9 x9, or x1 was like the value of first floor square footage, x2 was second floor square footage, and then year sold was x9. That's what I want to learn now. Does that kind of make sense? Like use these values, like find slopes for those, if you want to think about it as a slope. Like discover all these. So that if you give me a bunch of x values, right, you give me a new point in the space, right, you give me a new house, all their square footage values, I will predict for you the sale price. Does that make sense? I'd like to learn now, not just one slope and one intercept, but a bunch of slopes. You can also attack on an intercept if you wanted to, but we're just going to do the slope-based way. Okay, so, and that'll be good enough, honestly. So our goal is to find a bunch of slopes right now. Does that make sense? So where should I write that? Goal, find, and rainbow, a bunch of slopes. Not just one. That's really cool. So it's an interesting idea. And that just is kind of the generalization of linear regression to a bunch of values, a large dimensional space, whatever you're dealing with. Discover a bunch of slopes that minimize, right? The whole point of linear regression is the linear regression works is because it's minimizing the root mean squared error, right? We want to do the same thing for all those guys. Find inputs for like m, all the m values that minimize the root mean squared error of the sales price prediction. Okay, that's what we want. So, okay, let's do it. That's our goal. That's what we're doing right now. Scroll, scroll, scroll. All right. So we want to find a bunch of slopes. That's our goal. So goal. I'll write it here too. Oh no, I can't click and have it do anything. Something's wrong. Hello. There it goes. Goal. Find a bunch of slopes. Predict a bunch of slopes. All right. That's what we would like. And so what we kind of want to do is let's make a function. Just like you gave me some slopes, I'll give you the prediction. So I'll make this function. It's like, all right, call it predict. You give me a bunch of slopes, and you give me a new row of data, a bunch of attributes, not including the name, not including the sales price. You give me a brand new row. I'll do the imagine that slopes is the array of m, m1, m2, m3, all the slopes themselves, and it should be a triple one, isn't it? And then row is the brand new point in the space, is the x1, x2, x3 array, dot, 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 all the ones that you want, all right, to predict for. So what we would like to give back is we want to use that as prediction. We want to give back m1 times x1 plus m2 times x2 plus m3 times x3 plus dot, dot, dot. That's what I want to do. You give me the slopes separately. Yeah. You give me the m's separately. You give me the x's separately as arrays, because we don't know how many things we're getting. It's 9 this time, but that could change for new stuff. We want to give back, we just want to multiply them all to each other and then add them together. Okay, because that would be our prediction. That's our prediction. Okay, and so what we want to do, all right, you give me the slopes. I will multiply it by the row in array form if it's not already. So it's np.array to turn a row into an array. You give me, that's the multiplication part. And then I just want to add them all up. So I can say sum. That would work. Return all that. So if you give me some slopes separately and you give me a brand new row of x values separately, I will give you back my prediction based on those slopes for the x values. All right, and that's me calculating the right side of this equation. Yeah. That still remains to be seen. How do we find the right slopes? But like if you gave me the right slopes, the best slopes that go through all those data points in that multi-dimensional space, then we're good to go. All right. So yeah, here is that's our prediction. And so let's see. Do I want to type this out manually? I guess that would work. So here's the setup. Let's just pretend. So we've got our test table, right? This is we got a training set and a test set right now. We're going to use the training set to predict the slopes. We're going to use the test set to test, did our slopes work out properly? Like give all these things, check it against the real sales price that we're hiding. So we kind of want to drop this for a second. All right, so that's like our first thing that we're going to try it out. So test.drop sale price. Get rid of that for a second. And like this first row is the first thing we want to test our training data with, right? Test the slopes that we came up with. So let's call that this is like row 0. Give me that. Like that's our first thing we want to test with. That's like an example row. Example row is that. And we got that guy. We can also just let's make up some slopes for a second. All right. So here's a silly way to do it. You can say np.random.normal. You can draw from a normal distribution with average 10, standard deviation 1, and you can give it as many things as you want to give it. Like we want 9 things, right? This will give me an array of 9 numbers drawn from this normal distribution. It's just a bunch of random values, essentially, using a normal distribution. If you didn't know how many you needed, you could be like, example row, give me the length of that. Because we want as many slopes as there were x values. Yeah, that would do it for me. As many slopes as there are x values. So as many slopes as there are x values. This is just a random amount of slopes. We have no clue if those are good at all. They're probably horrible. Okay, those are my example slopes. And so I can use our prediction function now. So our prediction for this example row using those example slopes is the sales price that we think it's going to give back is example slopes, example row. We're predicting that that house is going to cost a little over $250,000 using those slopes, just for fun. Like 10 was a good value there. So cool. What was the actual value? So this is our prediction. The actual value that house sold for was like sales dot. It was test, wasn't it? We took the first row of the test table. It was test row 0, but like remember the sale price. Don't actually drop it. Give me the column sale price. Give me item 0 of it. That was the sales price of that house. Like that's the actual one. Does that make sense? It's like, here's our prediction. Here's the actual price. I guess we could have done it in that order. The actual price. Here's our predicted value for those example slopes. So our goal is to like find some slopes that are better than example slopes. Get the best ones that minimize the root mean squared error of the training set. And hopefully that also helps predict the values of the test set. That proves to us that we didn't just memorize the training set. So that's beautiful. All right. So I think that's what I wanted to say. Are we ready to find the best slopes? Does it make sense what we want to do? Let's make it happen. So we're going to use the minimize function. That's going to help us here. So, all right. We want to use the attributes of the test set, everything but the sales price, to predict their sales price, right? And by test, I think I meant training, but you get the idea. So we are training with our training set. We called it train. All these values we're trying to use everything but the sale price to predict the sale price. So the attributes are everything in the training set but, well here, that's train, right? There's the training set. Our attributes, train attributes, are everything in the training data except for the sale price. That's train.drop column 0. And then the prices that we're trying to make predictions for, the training prices, those are the things we're trying to predict. That's train.just give me column 0. Right? So these are the attributes we're using to predict the prices. Okay? It's got a bunch of rows here without the prices, and here are the prices we're trying to predict for those rows. Okay? That's what we need there. And then what we'd like to do is find the best slopes so that our predict function gives back the answer with the smallest error, the smallest root mean squared error for all these things. All right? So that's what we want. So, all right. Let's make a function called root mean squared error. For you give me some slopes, you give me some attributes that I'm trying to find the best slopes for, and you give me the prices. You give me the prices that I would want to compare against. Those are the real values. Like I want to use the slopes and the attributes to predict these prices as close as I can. All right, that's what I'd like. Dun, dun, dun. So this is going to give back the root mean squared error of trying to make those predictions. Okay. So that this is a function that calculates the root mean squared error when we're finished with it, at least. Root mean squared error for multiple linear regression. It's a very complicated topic, I know. We're getting through it though. So our goal is to minimize the output of this function by changing, like finding the best slopes. Okay, that's what we can vary that. Right? We want to minimize the value that this function returns, this to find the best slopes. Okay? So how do you calculate? All right, you give me some slopes. Like you come up with them somehow. You give me some slopes. You give me some attributes that I'm going to use these slopes to make a prediction with. Like I'm going to multiply these guys by these guys, the x values by the slopes of each of them. And then you give me the prices that are the real values, right? I want to see how far off I was. So I want to keep track of all the errors that I've made along the way. All right. This is how it's gonna work. Eventually, here, once we're done, like the goal is to say root mean square error of you give me some slopes, right? Maybe like the example slopes. See how well they did. Like we want to do that with the training attributes and the train prices. That's what I want to call it on. That's my goal. Okay. So you give me some slopes that you think are good. Here are all the attributes. Use the slopes to get some prediction values for each of those data points. And here are the real prices. See how far away you were. So for each row in attributes, that's a new data point. It's like this guy. Go use the slopes to make a prediction. See how far off you are. That's an error, right? For the next one, go through. Here's your next set of attributes, your next row in the training set. Go use the slopes to predict the sale price and see how far off from the real one you were. There's your error. Does that make sense? And we want to minimize the root mean squared error. So we'll keep track of all the errors that way. So for each thing in the attributes, we're going through it, and that's a row for me. All right. So let's see. Yeah. Let's get the indices of all the rows we care about. So for I in np.a range, and we've got, I guess I could say, yeah, I want like row I. Would that be useful for me? Yeah, because I want to go to each of them. So for I in np.a range, like I can do like the length of the attributes or the length of the prices. It doesn't matter because they're the same length. Prices is shorter to type. So, all right, for each I, that's an index into both attributes and prices, because like you have they're both as long as each other. It's like each one is in attributes was like this row, then that row. It's like as many rows as there were in the training set, and then prices was all the sale prices as well. So you have just as many for each of them. They're all together, and so all right, for each I value, I have an index into both attributes and prices right now. I can get a row out, and I can get a price of that row. All right, and they're separate for a second. So that is, I'll call that row. The row that I'm looking at right now is attributes.row I, and the price of that row, the actual price, let's call it that, is prices.item I, because it's that one's just an array. It was a column. Does that make sense? So far, it's a little weird and complicated, but you gave me an array of rows, or you gave me a table, I guess, of rows. I can go through each of them, and I can remember the price as well, and I want to use my slopes and that row to make my prediction and compare it against the actual price. See how far off I was. Okay, that's what I want. So there's the row, there's the actual price. My predicted price is, I have a predict function for that. You give me the slopes you're trying to use to make your prediction. You've given me your best guess of the slopes right now. Then I'll give you the row as well. Use the row, the attributes of that row, to make your prediction. There we go. And I think that's pretty much it. That's our predicted price from our predict function using those slopes. And we want to see how far off it was from the actual price. Okay, and that is a new error. So the error is it's always going to be I guess it could be either way, right? Because we're going to square it. And I forgot the order. Let's go back to the linear, because I think somebody, like I'm trying to copy a Berkeley professor right now and what they did, but I think they did it backwards, honestly. Do you guys remember if it's, is it actual minus predicted or predicted minus actual? So we're going to square. It doesn't really matter, but like for the sake of my brain, it's going to bother me. It shouldn't matter that much, but let's see, which one do we got here? Dun, dun, dun. It must have been in the next chapter. Yeah, probably. Was it 14? Or was it 15? It's probably 15. I will find it. Mark my words. Yeah, root mean squared error must have been in 15 then. Like, how far off was the prediction? Or was it 16? Minimize residual. Yeah, there we go. So it's more or less. So it's observed minus the predicted. Actual minus the predicted one, which should mean. Did we say that here too? All right, I'm gonna do it in that order at least. Okay. So error is, let's say that it's actual price minus predicted. How far off was the predicted price? So that's my error, and I would like to make eventually the root mean squared error. All right. So I'd like to do. I guess let's add that to errors. Can I do it in that way? Yeah. Root mean squared. So I want to eventually square those errors. So let's do that in that way. So here is errors gets that new error, np.append errors, giving that new error. And then, all right, I've gone through every row. I've calculated my errors array at this point. I've got all the errors. I want to calculate the root mean squared error. So that's take all the errors. You read it backwards, right? Root mean squared error. So we have the errors. We got to square them. So errors squared. We want to take then the mean, right? The mean of those. So that's mp.mean of all the squared errors. And then we want the square root of that. So to the 0.5. Is that how we do it? Yeah? Making sense? So that will give me, you give me some slopes that you think are good. You give me a bunch of rows, that's your training set. You give me the prices for those rows. I will use those slopes to make a prediction. I'll see how far off I was from the actual price. I'll calculate the root mean squared error of those predictions using those slopes that you provided. Does that make sense? There's so much going on there. It's weird. That's what we want. And I'd like to run it in this way. Like, all right, you give me some made up slopes. How good? How far off was it? It was apparently decently far off. On average, in this weird way, it was about like $70,000 off, $76,000 off, which is honestly not bad, but we could do better, perhaps. Okay, let's find the best slopes by minimizing the slopes input to this function. Does that make sense? Or like minimizing the result of this function where we can vary the slopes input. Essentially, that's what we'd like to do. All right. So the minimize function, if you remember it, it works like this. And we're going to use it. It just takes a function, and you can give it some extra things, and it like figures out what to provide. This is not very useful. I'll show you like the full way you could do it. I guess you could probably say minimize question mark, and it would show you all the ways you could make it work. Like there's some different options here, and we'll get that. We have to say array equals true because we're trying to make an array as well. But we want to call minimize, and here's how it's going to work. We want to make a function that just takes what we want to have it take. So let's do root mean squared error of the training set. So just taking the slopes, return the root mean squared error of using those slopes to predict the training set. That's just return our other root mean squared error using those slopes on the train attributes and the train prices, because we're always using the training set to do the prediction to see like the best slopes for these guys. All right. So this is just a function that takes the slope. You give me a good slope, your best guess of the slope, and I'll give you the root mean squared error of using the training set on those slopes to predict the prices. All right. And so that's just a function that takes one thing now, the slopes, and we can minimize that one input now. That's all. Okay. So I think that's what I wanted to say. So yeah, on our example slopes, same idea. If I call it with my example slopes, it's going to give back that same value. We want a better input than example slope. So we want to minimize that value. So minimize, how do I want to say this? Minimize RMSE train. Minimize that function where we can give it a starting point. It's a weird way that it does. I'm not going to test you on how minimize works in this way. It's like you give it a good first guess where I guess we can have it start there. Let me not do that. Let's see what that changes. I think we have to say smooth equals true because we're predicting a smooth function, and we're trying to output, the input is an array. It's not just an actual single number. So we have to say array equals true for sure. And I think, will that work? Please pass starting values. Okay, so when you say array equals true, you do have to give starting values. All right, so the starting values are our horrible example slopes. Find better ones starting from there. And it's off to the races. It's trying stuff. But once it gives something back, those are like the best slopes. All right, best slopes equals that. Best slopes. And yeah, let's let that think for a second. That's going to maybe take a while. But once it's done, it's going to give back an array of the best slopes that it finds that you could give as input to this RMSE train function that's going to like minimize the result of that function's return value, which is the root mean squared error of using those slopes to predict the training set's sale prices. So these are the values it came up with. Those are going to be the best slopes for using that kind of prediction. All right, and so let's print them out in a prettier way, because it's like this is the value you want to associate with the first floor square footage. That's that slope. This next one is the value you want to associate with the second floor square footage to predict the sales price, right? So that's how we were doing that. We're adding them all up, multiplying them together. So let's put those together. Can I really? Oh, that's disgusting. So here are the best slopes in that way. You can say, I don't know if I like this. Let me just paste it. It's a little disgusting. I'm not going to test you on it. It's like putting it in a cool way though. Dot labels. That is disgusting. And I wanted to see if we didn't need list here. Yeah, we didn't. So here is that in table form. It's disgusting looking, but it's like 80 was this is the number that you want to multiply the first floor square footage by. This is the number you want to multiply the second floor square footage by. And so on and so forth. Those are the best slopes. And we can figure out what was the root mean squared error of using those best slopes to predict the training set. It looks like it was only off by about $31,000 on average, its prediction. So that's decent. That's quite nice. Does that make sense? So we learned the best slopes to multiply each of these values by to predict. And this is a linear thing. Maybe it wasn't a linear output, but like we're just doing as linear as possible to make a prediction using these numbers. This is multiple linear regression. All right. So that's so cool. All right. And that's our root mean squared error for multiple linear regression. Are there any questions about that? It's a bit of a complicated idea, but hopefully this kind of helps. Like with linear regression, we were learning these two values. With multiple linear regression, we're just learning a bunch of values, one for each attribute. One for each attribute. We think of them as slopes in a large dimensional space. We're making what kind of looks like a line in a very large dimensional space. Beautiful. All right? And that predicts things well, apparently. Decently well. And so we can see now, we had this scatter plot just showing like the first floor square footage, like how well that did it, how well that correlated with the sales price. We can do the same kind of thing where we draw like how far off our prediction was from the real sales price. So because now we have these slopes. So let's do that for just the test set itself. I think that would help. And then you could probably calculate the RMSE for the test set next. But like that's a good stopping point. So I want to show you this. I don't care about you understanding the code. This is just like finding all the fitted values. So like this is our actual our predicted values, and here is the sale price, and the line is kind of like if it was perfect, everything would be on that line. So that's going to show how close our predictions are. Our predictions are quite close to what they really were, because they're close to this. Like if they were equal, like our prediction was the same as the sale price, they would be along this line. They're very close to that one. That's really nice. Okay, that's nice. You can also think about the residuals of this, because this is a linear classifier in a sense, right? It's a linear predictor. So residual still makes sense to want to do. Did I do that? Or did I mess something up? Test column test prices minus. We don't have test prices. Oh, we do. Okay. That's one thing that we didn't do yet. I guess we can do that next. So this was the root mean squared error for the training data on the best slopes. We can do the same for the test data and see how well it did. Okay, so let's try that. How do I want to do that? So the test, this is like the training price, the training attributes, the training prices. We can do the same thing for the test prices and the test attributes. And we can calculate the root mean squared error for using the training data to predict the test data. So there's the training stuff. Let's see here. We can do the root mean squared error of the best slopes using the test attributes. Oh goodness, yeah. I think I wanted to do this backwards. So yeah, I want to do this for test now. Test instead of train, sorry. There's a lot of things to keep in my mind at once. So this is, we want to use our best slopes now to predict the test set, all the stuff that we've saved away. All the stuff that we've saved away. Slopes for the test attributes, using the test prices to check how close they were. And that's the real root mean squared error. So it was a little bit bigger than the test, the training root mean squared error. But this is us using our best slopes that we trained using the training data, seeing how well they predicted the test values, using the test inputs and the test prices as outputs. So they're still about $31,000, $32,000 off, which is great. So that's quite nice. So that is a decent predictor. Yeah, and that's most of what I wanted to say. You can also do residuals for like how far off was it from, how far off were our predictions from the like the test prices. I think that's what I wanted to say. And you see that it's decently, at least for like houses that are reasonably priced. It's like a large blob, and that's what we should look for in the residual plot. That's showing us that our classifier, or not our classifier, that our predictor is doing a good job. But for large houses, it looks like we are we're predicting that like the difference is a bit high, right? So we're over predicting and underestimating maybe. So we're we're under predicting, sorry. So we're underestimating because like the difference was large. So actual minus predicted was a large value, which means that we underestimated. We're underestimating the price of the most expensive houses. But everything else, like once maybe like it depends on the neighborhood or something that we don't really know too much about. When they get so expensive, they just sell for weird amounts of money because they're like collector's items, houses that are that expensive. Who knows? But we do pretty well at predicting the bulk of the normally priced houses, which is great. But we do pretty well on the bulk of them. All right. So that's good news. That's great. I think that's most of what I wanted to say. So I am not going to test you very hard on this topic. This is a very complicated topic. In general, I kind of just want you to understand what the jump was from linear regression to multiple linear regression. And just like the way we did this was very complicated and weird. As long as you got the gist of it, though, I'm happy. Are there any questions about it? What we just did? We trained a linear regression tool. It was a multiple linear regression tool. It's wonderful. We found a bunch of slopes rather than just one slope and an intercept. You can also maybe think about adding an intercept to this. It would be just one more input now, which is cool. Cool to think about, and you can minimize that. Yeah, are we ready to see how we could use nearest neighbors for multiple regression? That's the last main piece of the puzzle here. So you can use k nearest neighbors for multiple regression in this way. You can be like, all right, if k equals 5, you got a new house in your test set. Like, go find the closest 5 houses in the training set in terms of all those numerical attributes. Go find it in that multi-dimensional, that 9-dimensional space. And they're all, the closest 5 houses will probably have a bunch of different prices. They'll range. But That means you can't like take the majority anymore. That doesn't make sense. Like they're all going to have different prices probably. The closest 5 houses to this new house point. But maybe you can take the average price of those closest 5 houses. Like go do that. That could work. Whee. And usually they'll probably be close by what that new house is going to sell for. Like, all right, this house exists right here in this space. Go find the closest 5 things to it. What's the next closest one? Say it's that one. I don't know. And go find the average of those 5 houses, something like that. So that could be used for prediction purposes. Does that make sense? That's honestly not as hard, I would say. So yeah, let's do the same thing. And I'll just do it kind of quickly because that is beside the point. I think you kind of understand what needs to happen, just like the code needs to be typed, and I will just copy and paste it. Nearest neighbors for regression. For some reason, the book only used a piece of the table. So that's interesting in itself. They only use the most correlated values, the most correlated labels. So let's do that. Whee. So they did this. Here is what they did. They made a test set and a training set, of course. That's using our old training set and our test set, but they took only a few of the labels. Boop. And so they only took first floor square footage, second floor, total basement square footage, garage area, and year built. They're going to use those values only to do the prediction. Like those were the highest correlated things. So that's going to make the prediction a little bit better maybe. And yeah, we need all these other things that we had before. We need our distance function. We need the distance between 2 rows. This was like, I think we called this all distances before, like give me the distance from each example in the training set, give me the distance to that, and here is what the actual values were. And then we can do like the closest, the KNN kind of thing. Give me the closest K neighbors to something. It's pretty much what we've already done. You can find our other functions that do those same things. So for example, here is the first row of the table. It was this one, I think. Yeah, I think it was that one. So like using these attributes, 1152 square feet, 0 second floor square feet, 1152 basement square footage. I guess it's just as big and wide as the first floor, which kind of makes sense. I don't know. This was its sales price. So use these values. Go find 5 houses or something. Go find 5 houses that are close to that in our training data. Go do that. That's what this is doing. Go find the closest to that new row, to that row that we're thinking about. Go in the training data, find the 5 closest things in that row, and give me back the average sales price. All right, that's what I want. Give me back use the sale price to do our distance calculation. All right, so that's what we're trying to get back. And I think that's what we want. That's the thing we're trying to predict. So forget about that is kind of what it's doing, I think. Yeah, we're just dropping that for a second so we don't use that in our calculation. And so here are the closest 5 houses to that one, and here are their sale prices. If we took the average of those, then that would make a prediction for us. So I think that's all that I wanted to say. So if you want to do a prediction using nearest neighbors, you could do this. You'd be like, all right, go do exactly what we did here. You do the closest, get all these outputs, give me the 5 closest sale prices to that house that you're looking at, this example house, this new point in the space that you haven't seen yet. Find the average of the sales price column, and that's our prediction. So we're predicting $281,700 that this house would sell for. Does that kind of make sense? You go find the 5 closest houses. If K is 5, give more, give less, whatever you want. Go find the 5 closest houses. In the training set for this new label, for this new piece of data with its attributes, its first floor square footage, second floor square footage, basement square footage, all that stuff. Go find the 5 closest houses in terms of all those attributes, and then average together their sales price. That's your prediction. It's honestly easier than multiple linear regression, I think. So yeah, that's that. And the actual sales price was... what did we call this? It was it was the test row with, it was row 0, right? And then it was item 0. Did I see that right? I think, yeah, no, something's a little bit off. Predict example that row. Let me paste it in. So I think I said something a little bit wrong. So it was supposed to be that. Unless, oh no, this was a bad prediction. Never mind, because our test set was a bit different than the other one. So it looks like we just did a really bad prediction for this house, but sometimes it's good. This time it's bad. If I made a new data set, it would be different, I think. So yeah. Unfortunately, we gave a bad prediction for this house, but in general, you'd probably get a decent prediction. So let me show you the residual graph for that. And then also how well it does in total. Because you can do the root mean squared error for these kinds of predictions. Boop. Let's do that one. And then I'll show you this plot. It will look different because our training set and our test set are different than when I was making the sample file. But kind of the idea is we can, again, make predictions for every house in our test set using our training set, find the root mean squared error of those predictions, and we can compare our nearest neighbor regression predictions to our multiple linear regression predictions and see who is the better one. That's what we want to do right now. So sometimes the house, like our prediction is way off, but sometimes it's better. Sometimes it's okay. So yeah, that's kind of how that works. It looks like our prediction in general is fine. If again, we're kind of underestimating the large, the high-priced houses, but it looks like nearest neighbor regression, it's a simpler topic. It did almost as good as the multiple linear regression for predicting the test set using the training set. And so I honestly want to find you a better example because this one was a way off prediction. Let's try like row 1 or something. Let's have row 1 be our example. Let's see, drop 0, row 1, go find the closest ones. And don't use that one, that is the idea. I guess that's fine. No, yeah, it's always going to be off a little bit. Actual sales price is now, it was item 1. There we go. Now it was 107 versus 168. So it's close for some of them, far off for others. Let's go back to row 0. Just unfortunately, this one was a way off one, but in general, it's predicting it pretty well. Okay, so yeah, it's not too much farther off than multiple linear regression. So yeah, that's kind of the setup. Again, I just want you to understand like the gist of it. So for multiple linear regression, you're finding a bunch of slopes and using those to predict the sales price. For nearest neighbors regression, you're finding like 5. Doesn't even have to be an odd number this time, actually, does it? You just find a certain number of houses or points in your space that are close by the one that's new. You forget about the sales price. You use those closest points to predict the sales price of the one you haven't seen yet, you know nothing about. Okay? So that's pretty much how you do it. The devil is in the details, of course. The code looks a little weird, but it's pretty much the same as what we've done. Is just instead of finding the majority, it's taking the average of the predicted value label. Yeah. Any questions about that or the difference between these two? We're doing multiple regression, so we're using a bunch of attributes to predict numerical things. It's a little complicated. I'll give you that. But yeah, if it makes enough sense, the last thing that I want to say for this chapter is sometimes you need to change units. So this is all that I wanted to say. So if you can imagine, you may end up with an issue if you have wildly different scales for your attributes. So think about this, right? Like here's our chronic kidney disease data set. Here are some points in that. We should have done this. Look at all these different points. Do you see how like the main difference of all these rows is the white blood cell count? Like those values are so wildly different from each other. They're very large. Like relatively, the distances from like 11.2 to 9.5, that's a drop in the bucket compared to 6,700 to 12,100, right? That's a huge difference. And so the distance between like this row and this row doesn't really depend on any of those. It's going to come down to what's the difference between those two values, right? Does that make sense? And so like this white blood cell count is going to have a huge effect on the distance between these rows. Does that make sense? It's going to have a huge effect on the distance between those two rows. It's not really going to even think about these distances because they are so small compared to the white blood cell count differences. Does that make sense? So the distance calculations are not as fair as they could be. You see that? So it's really just going to be looking at the difference between white blood cell count values because those are the ones that are on such a large scale. Does that kind of make sense? Like the distance is probably going to be almost this minus that. Same for all of them. It's like it's not even comparing the other ones. So if you want everybody to have an equal chance and be on an equal playing field, you should convert every column to standard units. Because then you know, just we've learned, right, the values are going to be within the range, like -3 to +3, if they're normally distributed, yeah? They're all going to be within that range. They're all going to have those kinds of distances. They're not going to be too far away from each other. They're all going to be on an even playing field at that point, which is wonderful. So they're all going to be turned into, like, now they're all going to be between, like, -3 and +3, or at least, like, -4 and +4, if it's not normally distributed. Like even those are pretty much all within that many standard deviations of everything. And so that's way better than being 1,000 off over here and like 3 off over here. That puts them all on the same even playing field. And with that, in general, maybe I can have you try that. We can think about it for a second at least. There's not too much time left, but that's the last piece of this puzzle. Let's do chronic kidney disease data set one last time using standard units. And I'll show you the difference. Dun, dun, dun. Yeah, I think that would be fine. And then we can finish the chapter in that way. So here, let's just find all the actual things that we need here. Dun, dun, dun. So here is our CKD table. Instead of what it used to be, here's the old CKD table. Old CKD table has a bunch of things in it. Oh, sorry, let's get just hemoglobin and glucose and white blood cell count. And then class. There we go. There are those. Look at the wildly different values. Look at the almost the same, on the same scale now values. You see that? And so the distance calculations are going to be a lot more fair if you're using this version of the CKD table. Does that make sense? Like that's the goal. And so let's see. We can do that evaluation. I think that would. We might as well just do it together. I think that's good enough. Let's make, for old time's sake, let's do a training set and a test set, and do our calculation for our accuracy for our prediction using this version of the table. Okay. So how many rows are in CKD? We've got 158. So let's do what we were doing before. Let's take just 2 of those. Let's divide it into 2. Right? So 79 in each. So let's make a shuffled table. Shuffled CKD is ckd.sample with replacement true. Oh, sorry, false. With replacement false. We've shuffled around the rows. Let's make a training set. That is shuffled ckd.take np.a range up to 79. So indices 0 to 78. And then the test set can be everything after that. Take index 79 onwards until the number of rows, which is 158. So go up to index 157. So, oops. Oh, sorry. That's got to be from there to there, just like that. So there's my test set and my training set. We can evaluate the accuracy of this with our function called evaluate accuracy. what do we need? We need probably that distance function right there. We need all distances. We need nearest. We need majority. We need K and N. And then we needed evaluate accuracy. We called that down here somewhere. We made it down here somewhere. I think it's that one. In theory, I can run it now. Let's try. Those are all the functions we needed. So I'll say evaluate accuracy of our training set, our test set. Now let's do like 5 nearest neighbors. Oh goodness, what have I not done? What can you not find? Apply, subtract. Oh goodness. Somebody's unhappy here. Let's see, was I supposed to get rid of something maybe? No, it's supposed to work. Func type, can't do it. Well, let's make sure our training set and our test set look normal. That looks fine. We have a class. Oh wait, no. We've gotten rid of a few things. Sample. Oh yeah, see, I reran it backwards, I think. There's CKD, CKD, CKD. There we go. I did something wrong with just the table itself, maybe? I had it be the old one for a second. There we go, yay. All right, that was confusing. So the accuracy of using the training set to predict the test set with K nearest neighbors of 5, where K was 5, it was 93% accurate, 93.4-ish percent accurate. And now we can do the same thing, but let's compare the accuracy against the original units. And I think, is that a good place to stop? So I can have you try that. Might as well. So here, let's go back to this table, just so that you can say you've done something today. I'd like you to try. Dun, dun, dun. So here is the here's the original table. We can say that CKD equals that. I think that's probably what I should have done for this other example. That is why I got that weird error. Boop. Yeah, that works. So that would mean now I can do it this way. Cool. All right. See if you guys can try. I'll give you like a few minutes. That can be the last thing we do today. Let me give you the code that we've written. And by that, I mean that. So if you refresh the page, you'll have everything. See if you can play all the functions using this final table. See if you can play all the functions in the right way to get the evaluate accuracy working one more time. See what the difference is. We got 93 for this one. You'll get a different one because you're going to make your own shuffled stuff when you run this one. So like compare what you get for evaluate accuracy on the converted to standard unit stuff. Compare that to the kept the original units and therefore only was considering the distances of white blood cell count values mostly. See how that compared. All right, so give that a try. I'll give you like a few minutes. See if you can find all the functions that matter so you can remember them. And then I think that can be how we conclude today, because that's pretty much the end of the chapter. I do have one last piece that we can probably do next week that won't affect any. I think it's one last good review. What are all the functions we need to make this happen? Dog and accuracy to run. What does it mean? It's distance, it means all distances, it majority, it means K and N, all those bad boys. They're all helping out each other. It should be decently different. So, one last crushed ice. Evaluate the accuracy of all those. Something like that. Can you find all the functions? Confusing. It does depend on the training set and the test set, but there should be a decently big jump in accuracy. And by jump, I mean drop. A few more seconds and I'll show you mine. What else do we need? All right, to end off today's very technical lecture, let's do one last time, evaluate accuracy of what we were doing, training set and test set for this table now. So I need to make a new training set and test set, don't I? With that new CKD table. I called it the same thing, but now it's got different values in it. And then I want to evaluate the accuracy of that again. Drum roll, please. Oh man, it's like 78% accurate compared to 94% accurate. See the huge difference there? It was really just trying to use white blood cell count, and that was driving the distance calculation and the prediction. That was not very good. We should be using everything in equal amounts, and converting to standard units gives us that. It's wonderful. So I hope that makes enough sense. Are there any questions about that idea? I think that's more or less it. So I'll try to clean up this this notebook when I give it to you. I'll try to put the functions next to each other at least. I'll do that as you're working. But that's most of what I wanted to say today. Are there any questions about k-nearest neighbors in general, multiple regression using either multiple linear regression, like finding a bunch of slopes, or using k-nearest neighbors and taking the average of the numerical value you're trying to predict now? You see how they're all working together and they're all kind of similar? So it makes sense to make one long chapter, but still, it's been a long chapter. All right, so with that, I kind of want to just show you that you should pat yourself on the back right now, because you've done well. You know pretty much the beginnings of machine learning at this point. That's a very fancy buzzword, but all like AI, right? AI is just machine learning. That's all it is. It's fancy machine learning. It's just another name for it. And machine learning is just data science. And data science is just statistics, right? That's all it is. And so doesn't matter what word you call it, you know it now. You know the start of it. You can go start to learn other kinds of algorithms if this interests you. It's really cool. It's not a big jump. It really is not a big jump to like be predicting text, because that's what AI chatbots do. Like looking at pixels, counting like how many cats are in this picture, like training a model that does that. That's honestly not the world's biggest jump. That would be the topic of like maybe 1 or 2 data science classes from now at like a 4-year college. So like you could be there. You could be there very soon, sooner than you might think. So that's really cool. I hope that feels nice to you. And I think that's more or less where I wanted to stop here. Project 3 is already out. It depended on all this stuff. We're finally through it. Hopefully it made enough sense. Towards the end, that was very technical. It's hard for even me to keep track of things, but we got there in the end. And that is where I want to stop for the day as far as the lecture is through. I have another last piece that's about ethics. That's not actually part of this chapter. It was just like a good place to put it there. That's where we can start next time, but it has nothing to do with like the project or anything. But that, my friends, is classification in a nutshell. If we are good, are we ready to talk about the final exam? All right. So it's going to be very similar to the midterm. You will find that at least. So reminder, you have a test coming up soon. I'll release the reminder for you to see now as you're looking through today's stuff. So I'm going to make the week 18 module available to you. So week 18 is the week that's just finals week, and you take the test and you're done. So that's all you do. So here, let me release the final info page and the extra credit assignment page. Eventually, on the day of the final, you'll come to class. You'll get on the big computers, and you'll click start just like you did for the midterm. But with every test also comes an extra credit opportunity, so I'll give that to you as well. So, all right, I just read this off of the syllabus, but the final is going to be in class on the Monday of finals week, 12/8. So December 8th, we're almost there, right? December 8th, the Monday of finals week, starting at the same time as class time. We only get an hour and 50 minutes to take the test. That's all we get. So it's still longer than the midterm, but we get like an hour and 50-minute window, and then we got to get out for the next class that might come in after us. So that's how that one's going to work. And yeah, the topics are going to be these. I'm going to try to test you mostly and focus on the stuff that I have not tested you on yet. The stuff from after the midterm topics. So these chapters, a little bit of overlap with the midterm, of course. Those chapters, these homeworks, these labs. There's only a couple that aren't out yet that deal with the last chapter. And then projects 2 and 3, those are the ones that were due after the first midterm. So yeah, that's what I'm going to try to hit hard. But honestly, of course, you should know that you have to know how to do table stuff. You have to know how to take samples. You have to know how to like make a histogram, stuff like that. Like everything's building on top of itself. We've been doing that all day long. So you should definitely expect to see midterm topics as well. But I'll try to focus on stuff from these chapters. Okay, so that's what's going to be on it. And the format's going to be exactly the same as the midterm. You can have like some fill-in-the-blank questions, some coding questions, and the rules are exactly the same. All right, you can make a cheat sheet where you can write on both sides. It's just like a printer paper size thing. You can write on both sides of that. You can use it while you're taking the test. Write as small as you like, but as long as you handwrite it. Can't print it out. And then you can have as much scratch paper as you need, but more or less you'll be using the Jupyter notebook as most of your scratch paper probably. So you get to use these 3 links. You can have your little temporary notebook that you shouldn't be relying too much on, like because it might, like if the internet goes out, this whole page crashes. So make sure that you're like copying things as fast as possible from this to the actual test on Canvas. You'll have that open, and you can have our 2 Python reference pages like this one and data science stuff. Like that page and this page, whichever one you prefer. You can have both of those open, or both, that's fine. But you get this one as well as those, just like you did on the midterm, to use and copy and paste from, but that's all you get. You can only have 4 tabs open, these and the test, okay? That's all you get as you're taking it, and I think that's all that I wanted to say. So again, I haven't taught this class before in the past, so at least you've taken a midterm with me now, so you kind of know how I'm writing my questions. It's a bit different than the Berkeley examples, but there's still the link to the Berkeley examples. I'll be looking there too, just for thoughts. I'll try to see if I can try to make some questions sound slightly similar, but they have the finals too from these semesters. So go look there. It can't hurt you, all right? But the format of our test is going to be different. Yeah. I'll try to use them as inspiration, perhaps. But you know that you know what the midterm was like. It's going to feel kind of the same. Okay, that's the goal at least. I don't want to trip you up too much. So that's what you can study with. And I think that's everything that I wanted to say about the final. We know when it is. We know what's going to be on it. We know what we get to do and what we're allowed to use as we're taking it. Does that make enough sense? Any questions about that? So that's important stuff. So we're all going to be in this room on Monday, December 8th at 3 p.m. to take the test. And then leap page. And then with every extra credit or with every test comes an extra credit opportunity. So there's one more test in the class. So here's one more opportunity to get some extra credit if you would like. It is just like for the midterm, you can make a review video for the final exam. So again, worth up to 5%. So make sure to get your stuff in. It's going to be due the midnight before for everybody, regardless of if you have extensions. The midnight before the test comes out. So the Sunday, December 7th at 11:59 p.m. is when you got to click reply or whatever it's called. So this is wonderful. It lets you study, and it's going to help your peers as well if you post something because they get to see it too. So I think it's a win-win. If you would like, you can make a review video where you talk about some examples of things that might appear on the exam. All right. So if you want to do it, here's what I want. So you make a little review video where you record your screen or something, and you're making up a bunch of examples of things that might appear on the exam. So you kind of maybe give a little mini lecture, go over some topics, come up with some examples, make some slides, make some diagrams, whatever you need to get your points across. So make sure to go over things. Don't just read the textbook or something. That wouldn't be extra credit anyway. But pretend maybe to be a professor, going over stuff, giving a little mini lecture. If you want just a quarter of the extra credit, just 1.25%, make at least a 10-minute video, maybe going over one good example, a couple small examples of things that you come up with that might appear on the test. If you want 2.5, half of the extra credit, make at least a 20-minute video, please, going over a few things. And if you want the full 5, go over a bunch of stuff in a 40-minute video. You don't have to edit it or anything, just stream of consciousness, go for it, like I've done here. What in the world? Cancel. Go away. With this software. I can help you learn how to use that if you have any questions. Just keep in mind that for extra credit, you got to do something extra. So you have to make a new code, write new code, make new slides, draw some new diagrams. Don't just go over your project answer, go over your lab answer, read off my slides, read off the textbook. That's not extra. You haven't done anything new at that point, right? So just make sure you're doing something new to get extra credit. You can ask me about it, bless you. If you have any questions, I can tell you if you're on a good track or not. But yeah, as long as you make something new and you go over it, I'll pretty much be giving you credit for it. Talk to me if you have any questions about that. OBS is the software that I use to record myself during lectures. That's one that all the cool hip streamers like to use. Zoom will also record for you if you want to do that. But yeah, if you want to do this extra credit assignment, I will help you. If you're not sure how to get the technology working, I'll be happy to help. So yeah, I think that's all that I wanted to say. So that's extra credit. Due the midnight for everyone, 11:59 p.m. No late submissions allowed. So get it in early if you want to do it. Any questions about that? All right, I think I'm done talking for the day. So that's when the final is. That's what you can do if you want some extra credit. On the day of the test, this will be released in the week 18 module. You'll come here, you'll click it, you'll start it, and that'll be that. I think that's all that I wanted to say. So yeah, I will stop the recording at least.